Okay, so in the last lecture, what we were discussing is this particular loss function, and what we saw was, like, this particular loss function is basically having two problems. The first problem is that this particular sigma that we have over here is basically, it creates the cost function as a non-convex cost function, which I had discussed in the last lecture. So because of this particular factor involved in this square function, let me see the thing first whether it's recording properly or not. I think it is. Okay, so the thing is, this loss function has inbuilt this sigma inside, so it creates the whole cost function as a non-convex cost function. So the function will be non-convex. So this is one problem. And the second problem is that this cost function actually is valid for all the ranges of y, because you can see here yi can take any value between there is no constraint on yi that it has to be this or that. As you can recall that in regression setting also, the yi's are of any value. There is no fixed value like it has to be in either 0 or 1 or something like that. So basically this cost function actually entertains all the values of y which are in between 0 and 1, or any value. So what we wanted to have is, we wanted to have a better cost function which can actually serve two tasks. The first is that this cost function, which is right now a non-convex cost function, can it become a convex cost function? That is the first priority. And the second priority is that the yi which we have over here, it is right now taking a wide range of values. Can we design a cost function which can take only two values, 0 or 1? So it should be like it should not take any other values of y except 0 and 1. So that is our target objective in defining a new cost function. But this one also will work, but it will create some problems, as I told you last time, because this is a non-convex function, so you may or may not get the global optimal solution. So that is the main drawback of using this cost function. So keeping these 2 points in mind, basically a new cost function was proposed, and this is the one which is the new cost function. And here you can see we have two different conditions, and the cost function is related to that two different conditions. The first thing that you will note over here is that we are actually finding the loss function for each and individual point in the data set. That's why I am writing a subscript I over here. So as the data set has I ranging from 1 to m, so I am calculating the loss for each of these samples. That's why it's L subscript I. And the second thing is, this loss function is divided into two parts. The first part is that if your labels are 1, as you can recall, it's a classification setting where your labels will be either 0 or 1. So that's why, based on that, if your labels are 1, we define a cost function which looks like this. And if your labels are 0, we define a cost function which looks like this. So these are the two different two different conditions for defining this particular loss function. So what it says is, if your labels are 1, actual labels of the data set are 1, then the loss function corresponding to the corresponding to that is this one, and the second is this one, if your labels are 0. So if you recall, earlier we only had this. If you see in the earlier cost function, we only had this, but now what we are doing is we are modifying it by multiplying it with minus log in the first setting when your label is 1, and with minus log times 1 minus this when your labels are 0. So now what we will do is, we will try to write these two in one single statement and see whether we are able to do it or not, because these are two different conditions. We want to write it in a single statement which can entertain both of these conditional expressions into, which can combine these two conditional expressions into a single statement. So if you do that, what you can do is, you can actually combine these two together into one single statement which looks like this. So here you can see what we are doing right now is we are actually writing the loss function which is conditional into a single statement which is over here. So maybe someone can ask, like, how come, can we prove that this is particularly, can we decompose this into separate individual components or not? So it is very easy to do it. So if you, let us suppose, if you want to evaluate this particular expression for yi equal to 1, if you put this yi equal to 1 here, then you will see that the corresponding loss function Li theta will be minus log sigma x dot I theta. This particular expression, green expression, will reduce to this expression, and this is the same expression which you have over here. If you see on the top, you are having that same expression over here, and this is when your yi is equal to 1. So if you put yi equal to 0 here in this expression, what will happen? This will go away, and you will only be left with the second term, which will be minus log of 1 minus sigma xi theta. You can substitute the value of yi equal to 0 here, and you will get to know that the corresponding Li theta that you will get is minus log of 1 minus sigma xi theta. So this shows that you can combine these two conditional expressions into a single expression like this. So this is basically our new loss function which we will be using. Earlier, in case of earlier we were using this one which we were motivated by using through linear regression loss function. So if you recall, this is basically similar to the linear regression loss function, except that this sigma was not there. But right now what we were trying to do is we were trying to use sigma also on top of it, and we were trying to implement this linear regression concept, the cost function that we derived from there, onto the classification setting also. But we found out that because you incorporated this sigma into this particular factor, this particular cost function, which was convex in case of linear regression, became non-convex in case of classification setting. So that is why we are coming up with the new cost function, which is this one for classification setting. This is the new cost function, and it is also called as binary cross entropy loss function. So let us see what it tries to tell you here, like in terms of the physical interpretation, what it is trying to say. So if you focus on this particular expression first, which says that if your label is 1, the corresponding loss function that we have is this one. So let us interpret what this is. So what this is like, what it is saying is your loss function will be minus log of sigma xi theta if corresponding label is 1. So if you try to plot the curve for this particular because this is again a loss function, this is basically a loss function, right? So if you plot this loss function L with xi theta here, so what you will get is you will get a curve which looks like this. So this is basically minus log x curve. So there is nothing rocket science here. So if you try to plot minus log x, it will look like this. So the important part is, like, we have to restrict ourselves in between 0 and 1. We have to restrict ourselves in between 0 and 1. Anyone can tell me why we want to restrict ourselves in between 0 and 1? Okay, so the reason why we want to keep that values in between 0 and 1 is because you are actually interpreting the model as a probability score. So if you recall last time when we discussed, whenever you interpret the value, it is in terms of the probability, and that's why we are restricting our range in between 0 and 1. We are not going beyond 1 because probability ranges in between 0 and 1, it doesn't go beyond that. So that's why we are actually interested in this range, which is in between 0 and 1. So the important thing here is this particular loss function, how it is helping us in getting this particular basically we are trying to interpret why we have selected this particular curve. So if you see here, if your labels are saying that your corresponding y is 1, and if your machine is interpreting the value, because this is the value which your machine will be predicting. So these are the output values which your machine will be predicting from the machine learning network. So basically, if your output is this one, which is 1, and your label is also 1, so that means there is no error incurred. Basically, there is no error incurred, and you can say that the loss corresponding to that type of thing will be 0, because your machine is also predicting value 1 and your label is also 1. So because of that, things are pretty fine because there is no error involved. But in case if your machine predicts a value of, let us say, 0.7, then at this point it is giving you a value of 0.7, but the label present in the data set says that the value is 1. So definitely there is an error, because machine is saying value 0.7, the actual labels are 1. So you have an error of 0.3 here. So obviously the loss is more compared to the loss which you had earlier, which was close to 0, but now the loss is more because the value that you are getting is very far away from the value of 1. Similarly, if your machine predicts a value of, let us say, 0.3, then you can see the loss corresponding to that will be much higher compared to this loss or compared to this loss. So you can see now the difference between 1 and 0.3 is 0.7, which is much higher compared to the other losses which you have. So that means your machine is performing poor here, because it is giving you a prediction that the labels are 1 with the probability of 0.3, but it is actually having label 1 with probability of 1. So basically what happens is you are trying to create a difference in between the prediction as well as the actual labels. You are trying to actually quantify the difference in terms of the loss function. So here you can see that the loss function that you have designed is actually for y is equal to 1. So you can see if the machine predicts close to 1, it will have 0 loss, and if it predicts a value of 0.3 or 0.4 or 0.5, which is different from 1, it actually has a loss function which keeps on increasing. So that is why this is the physical interpretation for this particular part when your y is equal to 1. And you can see this particular loss function is actually a convex loss function, because there is no curvature like this over here, which is non-convex curvature, but you have a simple curvature which looks like this. So it's a convex function with minima at this point. So you can see if you put your gradient descent at this point, it will actually go easily to the minima. But if your curve is like this, then you can easily see that it will be a non-convex function, which was happening in the earlier case. But here now it's a smooth convex function. Whenever you initialize your algorithm at any point, it will slowly go down and gradually stop at the minimum value. So that's why this particular cost function is a convex cost function, as you can see over here. Similarly, in the other case, when your function is this, if you see here, if you plot this function, it will look like this. So it is 0 here, and then you have 1 this side. So if you plot this function, it looks like this. And here what it is saying is that if your labels are 0, actual labels are 0, and if your machine predicts a value 0 here, then you can see the loss function, which you are writing this one as the loss function, right? So the machine is predicting this 0, and actual labels are also 0, so the loss is 0. But if your machine is predicting a value of 0.8, but the actual labels are 0, then you can see the loss is increasing also. So here you can see as you are moving away from y equal to 0, the loss is continuously increasing. So again, this is also convex and it's not non-convex. So you can see that if you combine the two parts, this part and this part, so basically if you combine the two convex functions, the summation will also be convex. So Li theta, which is basically summation of this and this, is also convex. So this is the physical interpretation of why we have selected these two functions when your labels are 1 and 0. So if you have any questions you can ask, otherwise I will move forward. So this is basically the combined loss function, which individually I have explained you that the first one what is the interpretation and for the second one what is the interpretation. So if you have any questions here you can ask, otherwise I will move forward. Okay, so here you can see this is basically for all the individual elements I. So here you can see I is there. So this is for each individual data points in the data set. But you know that the data points that we have in the data set are from 1 to m, which we have already, we are sticking to this particular symbol m, which indicates that how many samples you have in the data set. So this is for a particular data point we have defined the loss. So for the combined loss L will be nothing but average of all the losses that you will evaluate for 1 to m. So here you can see the combined loss function L will be minus 1 by m, and then you actually write Li theta, which is the loss function that you have for the single ith element. So you actually write this. This is summation I running from 1 to m minus 1 by m. You are just writing it like this. So this is the combined loss function, and this is actually convex as well as it caters to the value of yi being 0 or 1. It will not take any other value in between 0 and 1. It is defined only for the labels which are either 0 or 1. So now once we have defined this loss function, new loss function for the classification setting, how to obtain the optimal values of theta? It's very easy. As you can recall, the gradient descent that we were using last time, which actually updates the new value of theta I. So this is basically new value of theta I, which is equal to the old value of theta I minus alpha times the derivative of the loss with respect to the theta I. So this you already know from our previous exposure to gradient descent. So the important part is that how to define this loss function, which we have already defined here. So now what you have to do is you have to take the derivative of the loss with respect to these theta parameters and plug in this equation to get the equation for parameter updates using gradient descent. So this is the derivative of the loss with respect to theta I, which we have to calculate. So if you the next challenge is how to calculate the derivative of the loss with respect to theta I for this particular thing. So this is actually important. So let us do that. So before going there, let me tell you one thing, that we have this sigma inside. We have this sigma inside. So if we take the derivative of this sigma, because sigma is defined like this. So if we take the derivative of the of this sigma x dot theta with respect to theta, you can easily see from this derivation that the derivative of the sigma, which I am writing as sigma dash x dot theta, it is nothing but this expression, which is sigma x times 1 minus sigma x. So where sigma x is nothing but this. So basically it has to be not sigma x, it will be sigma x theta. So it has to be this. So there is a mistake here. So basically sigma dash x theta will be nothing but sigma x theta times 1 minus sigma x theta. So this is basically the thing which you have to keep in mind. Now once you have this loss function over here, so what we do is we want to calculate the derivative of the loss with respect to theta j. And note that this j will be running from 1 to n, because n are the number of features that you have for this particular problem. So it will be running to 1 to n. So that is important. So here you can see now we have this expression which is given over here. If you take the derivative of the loss with respect to theta j, it is very easy to do here. You can see that it will be like, yi times, if you take the derivative of the loss with respect to theta j here, you will get this expression, and for this expression you will get this expression here, and then you have to take the derivative of the loss with respect to theta j for the expression which is inside here. So this is again you have to evaluate, and once you cross multiply these terms here and take the bottom part over this side, once you do that you will get this expression times you have this which is actually coming from the derivative of the derivative of this particular expression with respect to theta j. So you can clearly see that what you will get here is xi with the subscript j here, because you are taking the derivative with respect to a specific theta j. So if you have theta 0 plus theta 1 x1 plus theta 2 x2, so if I tell you to take the derivative of this expression with respect to theta 2, then x2 will come out. So similarly here, when you are taking the derivative with respect to theta j, the corresponding xj component of xi vector will come out. So this is basically that difference which is over here. So once it is there, then what you can do is you can actually substitute this value which is over here with the value which is given over here, which we have already derived, and this is the one. So once you substitute this value which is given over here, what you observe is this denominator will actually cancels out with the numerator. So if the denominator of this cancels out with the numerator, the only thing that is left is this expression which is over here. So this is the derivative of the loss with respect to theta j. So once you have this derivative of the loss with respect to theta j available, you can plug it into this gradient descent equation which is given over here, and you will get the updates of the value of theta. So your updates of theta will be evaluated. You can evaluate that by using this expression. So this is basically individual elements of theta j. If you want to update, you will do it through this expression. But if you want to vectorize it, as I told you last time also, that vectorization is the main important aspect, because we want to vectorize, because we want to speed up the process. So what we will do now is we will try to vectorize this expression which is given over here, which we can do like this. So here you see, once you vectorize it, what you are doing now is you are replacing this particular thing by this xi transpose. So I am just converting this into a vector of x dot I transpose, and once you do this and you keep this side, once you do this manipulation, what will happen is your output will be a vector of thetas. The dimensions of that will be n plus 1. So by using this expression, you can actually get all the values of the theta at one go. Whereas in this case, you are getting individual values of theta all the time, and then you are doing individual gradient descent. But with this expression, you can get all the values at one go by multiplying the transpose with this expression. So you can use either this or this expression to evaluate either this expression. So you will go with individual values of theta one by one and get the answer, which is a slow process. Or you can use this expression here, which is the vectorized implementation, at least at one level, where you have transformed this into a vector like this, so that you can actually speed up the process a little bit, but it will not be increased too much because of the factor which is available here. So this factor which is here, it is actually creating a trouble, because your summations are running from 1 to m. So if you recall, your m is basically very large in data sets. In the practical data sets, there will be million images or million samples. So the problem is you have to sum these million samples. Once you sum them up, then only you will get the value of theta. So this is the major drawback that we have. So one vectorization we have already done inside by transforming this expression into the corresponding vector, but now another vectorization is required which can remove this summation. So in order to do that, what we do is, in order to remove this summation, we again go for this expression. So if you see here, this expression is actually, the summation sign is gone. If you see this summation sign is gone, and you can see now there is no indexing of yi at any of them. There is no yi, there is no x dot I. All of them are matrix. So all of them are matrix representations. So now this summation is gone, and if you multiply this expression with this expression, you will get the corresponding loss, and for the whole data set. Here you had to sum them up for all values of running from I1 to M, but now in this case no summation is required. It is basically evaluated at one go. So there is no summation required for this particular setting. So now if you take the derivative of this new loss function with respect to theta, it will be, you can evaluate yourself. So there is no, there is no rocket science here. So this is just the derivation. So once you evaluate the derivative of the loss with respect to theta for this expression, and when you solve for this particular expression, what you get is this particular loss function with respect to theta given like this. So here you can see now that the important part that you can observe here is that this is basically the complete vectorization code that we have here. So this is the complete vectorization code where there is no summation involved. It is only matrix multiplications. So this is the loss function that you will get, which is a complete vectorized version of this loss function, which is over here, where you have summation also, where you have these xi's also. So we want to evaluate this loss function in one go. So the corresponding the derivative of the loss with respect to the theta is this. And if you plug into the gradient descent, then you will get this answer. This is the answer that you will get when you plug this particular expression into the gradient descent. And if you see, this expression is quite similar to the expression of linear regression, but the only difference that you have here is that your y's are restricted in between 0 and to 0 and 1 only. So it is either 0 or 1. So it is restricted to these two values only here, but the expression is same. The one which you got from the linear regression, the same expression is there, but the only difference is, first of all, you have this sigma, and the second is your y is restricted to either 0 or 1. So this is the gradient descent in the vectorized form for this particular loss function, which is the new loss function that we have defined for your classification setting. Any questions here? Anyone? Okay, so this is basically the derivative of the loss with respect to theta that we have calculated here, and you can see it's a vectorized implementation, and we got the corresponding thetas which are similar to the regression setting, but the only difference is this sigma is there, and then y is actually limited to either 0 or 1. And this is again showing you a simulation plot where you can see how you are actually fitting to the data points which are given over here. So there are few data points here which are 0, and some of them are here as 1. So you can see how the curve is nicely fitting into the data points which are over here. So even this is the contour plot which is showing you how the loss function, this is basically not g0, this is loss function of theta 0 and theta 1. So here you can see it's theta 0 and theta 1. So you can see how loss is actually going from this point, initialized at this point, and hitting to the minimum value here. So now the important question that comes to mind is that instead of the labels being 0 and 1, which we were telling last time, is what will happen if the labels are between -1 and 1? So will there be any difference or not? So let us answer this question, that if you have 0 and 1 labels, which we have already discussed in our earlier slides, if the label changes, like if the label becomes -1 and 1, will the story be different or not? So if you see this picture here, so what it is showing you is the earlier problem statement, which started from that you have these elements over here. Some of the data points are here with the value of 0, and some of the data points are here with the value of 1. This we have already discussed last time. And what we observe is that if you project these data points onto a one-dimensional plane, here you can see you are right now on two-dimensional plane where you have x and y coordinates. But if you want to project it onto a single line, which is x over here, then what you see is the projection of these points onto a single line x will look like this. So you can see some of these data points will be projected onto the line, single line like this, and these points will be projected onto the line like this. And now you can see in the two-dimensional plane, when it is projected to a one-dimensional line, it will be projected as a cross, the separating boundary basically, because you have a separating boundary like this, right? So this separating boundary which separates the two data points, these data points, the boundary, when you project it onto a one-dimensional plane, it reduces to a point. Similarly, in the two-dimensional case, you can see now when you project these points onto the in the three-dimensional space, when you have these data points, when you project it onto the two-dimensional space, then what you get is a line as a separating boundary. This is clearly visible from here. So these points are actually projected onto the red points, and these points are projected as blue points. And the separating boundary in between these two planes is basically a line in the two-dimensional plane. But now if the labels are -1 and 1, you can see from the diagram itself that there is no change in the interpretation, because even if the labels are -1 and 1, we should get the same type of results, because you can see from the diagram still remains the same for case of -1 and 1. So let us see whether the interpretations are same or not, even when the case is from -1 and 1. Like earlier the labels were 0 and 1, but now if I change the labels to -1 and 1, will the story change or will it be not? By seeing the figure, we can see that the story will still remain the same. There will be no problem, you will still get the answer, because you can see the interpretation in the xy plane as well as in the single x plane remains the same in both the situations when the label is 0, 1 or -1 and 1. So if I want to model this particular data set, which has a range between minus and 1, earlier it was 0 and 1. So what we did is we started out with the unit step, and we defined that let us model it by a unit step like this. So in this case, our function should be like this, which has a -1 here and a 1 here. In order to model this particular data set, ideally we will be using 3 different approaches. First is this Signum function. So the Signum function actually ranges from +1 to -1. As you can see from these data points, it is ranging from -1 to +1. We want to fit this curve. So one approach is to use Signum function, and you can use this particular loss function for Signum function. But the important thing is, if you recall our classification story, at that time we were using here unit step. Now we are using Signum function. But whatever disadvantages we had for that case where we used unit step, whatever disadvantages I told you at that time, the same disadvantages will hold for this particular function, this particular loss function also. So you can look into our earlier lecture on that. Whatever loss functions I have told you for using the unit step here, the same will be applied for this loss function also, which is Signum function. The second approach, basically, again, after using the unit step, I told you that this is the hard separating boundary. Let us approximate it with a softer version, and this softer version was sigma, which we started out with. In the similar way, the Signum function can be approximated by tan hyperbolic function, because that tan hyperbolic function ranges from -1 and 1. So we will approximate this signum function by tan hyperbolic function. So tan hyperbolic function is basically a smoother approximation to signum function. As sigmoid is to the unit step, sigmoid is basically a smoother approximation to the unit step. Tan hyperbolic is actually a smoother approximation to signum function. And the loss function that you will get when you use tan hyperbolic function will be this. And the same problems that we discussed in case of using sigma here, we told that this sigma is creating a non-convexity in the classification setting, as well as your yi's are ranging between all ranges. They are not restricted to 0 and 1. So because of these two reasons, for the classification setting, we will be changing this loss function also, but I am just telling you different type of ways of approximating your labels which are -1 and 1. So these are the two different ways. Same logic, same approach, same approximations, but using different functions. In the earlier case we were using sigmoid, here I am using tan hyperbolic. So everything is same except this the concepts are same, but only the functions will change because your labels are changed. It's not 0 and 1, it is between -1 and 1. So because of that, your loss function also changes, but the overall understanding of the loss function will be the same, and it will have same drawbacks as it was in the case of classification setting where labels were 0 and 1. Same stories. So now we will again use binary cross entropies here to address this problem of -1 and 1. So the only difference now is, in the earlier case, when you were using binary cross entropy, the labels were 0 and 1, but now here the labels are 1 and -1. So the problem is how to define a new loss function for this particular new strategy. In the earlier case, this particular loss function which we have defined here, this one, this is actually valid only for labels ranging which has labels either 0 and 1. You cannot use it for any arbitrary labels. But now this particular loss function is different from that because your labels are changed. You cannot use that same loss function which you have used in case of binary cross entropy where labels were 0 and 1. So we have to find out another way of solving this particular loss function. So here it can be also shown that if you put -x into sigma, if you put -x as an argument, it is nothing but 1 minus sigma x. So this is again another identity. You can prove yourself. I will not prove it. And the thing is, if you put -x in the argument of the sigmoid, it is nothing but 1 minus the sigmoid of x. So this you can prove yourself. So if you we will be making use of it. So here you can see now this 1 minus, if you say that this particular argument is x, then 1 minus sigma x can be replaced by sigma of -x. So this particular argument inside can be replaced by sigma of minus x dot theta. So what I'll do is I will rewrite this function again, and you can write it like this. So here what I am doing, I am actually using this particular expression to replace the argument which is inside here. So this is the way which I have written it. So this is very simple. I am just using this particular expression. So now the second step is how to combine these two conditional statements into single statement. The way which we had done it for the binary cross entropy, same we have to do it for here. So in order to do this, what we do is we combine these two expressions into a single expression using this expression here. So here you see we have log minus log sigma yi I have multiplied with xi theta. So the important point is how come this particular loss function is equivalent to this and this. So this is very easy. If you replace yi by 1, what you get is minus log of sigma x dot theta, which is same as this. And if you replace yi as minus 1, you will get minus log of sigma minus x dot theta, which is the same as this one. So basically, if you write yi as plus 1, this will be minus log sigma x dot I theta, which is the same as this expression. And if you write yi as minus 1, you will get minus log of sigma minus x dot I theta, which is the same as this expression. So you can combine these two loss functions together into a single loss function like this. This is the same way we have done it for labels 0 and 1. In the similar way I am doing it for labels minus 1 and 1. So now once you have this, you can actually write the combined loss function running from 1 to m, because this is for an individual value of I. But now you have to run it for 1 to m, the whole data set. So this is the expression for it. And you can substitute this value over here and you get this expression. This is the loss function, the modified loss function when your labels are minus 1 and 1. If your labels are 0 and 1, the binary cross entropy loss function will be there. But if it is between minus 1 and 1, then the loss function is this. This can be, you can incorporate this minus inside. So once you incorporate this minus inside, you will get this answer, which is nothing but minus log of x is log 1 by x. And you know that your sigma, if you put an argument this inside, it is nothing but 1 upon 1 plus e to the power minus this. You know this is easy, right? Sigma x is nothing but 1 upon 1 plus e to the power minus x. So I am just substituting instead of x this argument. So you can write this expression. So once you have this expression, you can actually substitute it here, and what you get is this. So this is the loss function that you have for the labels 0 and for the labels which are ranging from minus 1 and 1. So this is the loss function for that. And it is also called as softmax cost function for logistic regression. We will discuss what this softmax is in the next lecture, but this is you keep this in mind that this particular expression is a softmax cost function for logistic regression. We will discuss this and we will come back to this equation again. So keep this in mind that this is the softmax cost function. So now if I take the derivative of the loss with respect to theta, you can evaluate yourself that it will come out to be this. This is the derivative of the loss with respect to theta. And then it is easy, right? Then you have to write the theta as theta minus alpha times the derivative of the loss with respect to theta. So this you can actually substitute this value over here to get the combined theta using the gradient descent. And note that this is the unvectorized format, because here you have this summation running from 1 to m. So you have to actually vectorize it by removing this summation sign and make it a complete vector format. So this is actually showing you the results for that. And here you can see now the labels are between minus 1 and 1. So your decision boundary is actually like this. Earlier the labels were 0 and 1, so decision boundary was like this. So this is the label story for minus 1 and 1. This is the expression for vectorized format. I am not going into the details of that. You can check yourself what it is. You can implement yourself this particular expression if it is in a vectorized format. So what you will get is complete theta in one go without without this summation which is over here. So this is the vectorized implementation of this. So this is basically the story. So basically group 5 has to write up to this point. So because today's lecture is I'm keeping up to this point only. I will go to the next lecture next points later on, but the important thing is this particular expression is for minus 1 and 1, and for 0 and 1 I have already shown you the derivative of the loss with respect to theta and how you are doing gradient descent for that. So any questions here related to this discussion? If you have any questions, let me know. Otherwise, today we will close this class. Any questions? So your next lab session, basically you have to submit your perceptron algorithm, because it's already 2 weeks time I have given you. So so by next week you have to submit your perceptron algorithm thing, and I will be discussing that perceptron algorithm in the next class. But you can watch my earlier lectures also on that, and if you wish, and try to finish that assignment as early as possible. Any questions?
No, sir.
Okay, then thank you so much for attending the class. Bye.